Sorry, this is part 3 of the video, and the TAR, I think I mentioned having the air as a ratio with the air on top and the phantom on the bottom. It's actually the other way around, so I'm sorry about that. So since we're looking at this particular example here, we know what the TAR is, we know what the area factor is, and we know what the dose rate, the reference dose rate is. Because all of these were told to us here, and we know what it is here. And let's see, where's that last factor? Struggling to find that last factor. I know it's here somewhere. I know I saw it. There it is, right there. It's right in front of me. All of those factors being put in, we end up with, since it's a cobalt unit, we're going to end up with time, and that's 1.09 minutes. The linear accelerator, if we're using the same approach, we've got our prescribed dose up here. We have our centigrade per mu. We have the TAR here as well. Looking up for all of these, we end up here with our dose rate, and we end up with at 12 cm depth what the TMR is. Well, in this case, I mentioned it as TAR. I don't know why they go from TMR to TAR. That should be the same regardless. So they put all of this information in, and you come up with 119 monitor units. I will work some of the problems here at the end because I think that would be good for you guys to go through. Calculating entrance dose and exit dose from parallel opposed beams with equal weighting. So let's say that we've got field A here and field B here. We're putting our isocenter right here. We've got a distance across here of 24 cm. So our distance from here to here is going to be 12. And the same here to here is 12. From there to here is 12. So if we're looking at field A and it delivers 100 centigrade at the isocenter, the TMR at D max, or 2.5 cm depth, since we're looking at, it doesn't give us the energy, but I suspect it's a 4, is 1.0. The distance at this point is 100 cm minus 9.5 or 90.5. The dose is higher at this point by the inverse square factor at this distance. And so using equation 3.1, the inverse square factor ends up giving us this. So in other words, since we are closer to this than what was calibrated at 100, we introduce the inverse square factor here to sort of dial down the amount of dose that we're going to need. So, and it says, notice that the reference point in this calculation is an isocenter, while in a fixed SSD technique, the reference point is typically at D max. So the dose at a point on the central axis is going to be found by basically, if you take the mu equation and you just have the dose over on this side, it usually has a denominator here with a bunch of other factors in it. Those factors got moved over here. So you've got mu, and then you've got the centigrade per monitor unit, and then you've got the TMR, TAR, TPR, however it's measured, and then the inverse square factor. So the dose here at this field is going to be 119 monitor units, which we determined here, times 1.03 times 1 times 1.221. So that gives us 150. Centigrade per monitor unit, this distance would be slightly less than 1.03 because the field is smaller, but the shorter distance to the collimator causes somewhat more scatter at this point. So in this example, we assumed that these factors cancel and that the centigrade per monitor unit is the same at 90.5 and at 100 cm, except for the effect of the ISF. And so the dose at the same point for B is found from equation 4.36. So basically use the same equation for the other. So the TMR for field B is 0.616 at 21 and a half cm depth. The distance from field B to this point is 9.5 cm longer than to the isocenter. So it is at 109.5 cm. The inverse square factor is 100 divided by 109.5 squared. Plugging all of that information in, you find out that it's delivering 63 centigrade. So the dose at D max is 150 from field A and 63 from field B, which gives us a total dose of 213 centigrade, 6.5% higher dose than what you're seeing at mid depth. Let's see. Trying to figure out exactly how much further. Okay. Okay. So calculating dose from parallel opposed beams with unequal weighting. So in an isocentric technique, it is customary to normalize the dose at the isocenter and weight the beam at this point. It's not always the case, but yes, it does happen. In this example, where two parallel opposed 4 MV beams are used to treat a right parotid tumor, which you don't normally see now. It is assumed that the isocenter is in the patient's midline. The SAD is 80 cm and the fields are 9 by 14. The beams are weighted 2 to 1 from the patient's right, meaning that 2/3 of the prescribed dose at the isocenter is delivered via the right field and 1/3 on the left. Patient's diameter or separation is 13 cm and the centigrade per monitor unit at 80 cm distance is 1.01 without the patient present. So from table 8A.4, the TAR at 6.5 cm depth is 0.892. The prescription is for 180 centigrade to be delivered at isocenter. The MU necessary to deliver this treatment can be found from the fraction of the prescribed dose divided by the calibration factor times the TAR. Since the dose at the isocenter is different for for these two fields, they're calculated separately. So you've got 2/3 of this calculation is going to be delivered using the right. 1/3 of this is going to be delivered using the left. Obviously, you are seeing differences here in the TAR, but the centigrade per monitor unit calculation is going to be the same. So in the following example, the same treatment is to be delivered, but the isocenter is moved to 4 cm depth from the right side. Rather than a midline, they're going to shift it 4 cm this way. The weighting, the field size, and the SAD remain unchanged. The TAR tables from 8.4 are the ones that are going to change. 9.977 at a 4 cm depth and at 11 cm depth, you're looking at 0.738. And the calibration factor is not changing. So the MU necessary to deliver 2/3 of the prescribed dose through the right is going to be done with this. The 1/3, which is delivered to the left field, is going to be this. So the calculated number of MU decreased from the right side and increased from the left side when compared to the previous example. Shifting the isocenter farther away from the midplane and suitably weighting the beams could result in the same MUs from both sides if you continue to make that adjustment. So in the next example, a tumor in the posterior aspect of the right lung is treated via parallel opposed oblique fields. And why would they be oblique in this case? In this particular case, they might be wanting to stay off the cord in order to be able to hit this to the dose that they want. So they're going to be using 4 MV photon beams. The fields are going to be 10 by 10, and the SAD is going to be 80 cm. The depth from the anterior skin surface to the isocenter is going to be 23 centimeters. For the posterior skin surface, it's going to be 7. TARs are given here, and they're taken out of table 8.4. The fields are weighted 2 to 1, favoring the right posterior oblique. This one. The centigrade per monitor unit is 1. The prescribed dose is 300 centigrade at the isocenter. So we go through the calculations here to figure out the weighting is going to be 2/3 towards this field, 1/3 for this one. They go through the computations here, and they figure out you've got 231 here, you've got 244 here. If you're calculating entrance dose and exit dose for parallel opposed beams with unequal weighting, the entrance and the exit dose at D max of each field are calculated as well. So you've got the dose at depth of maximum dose RPO field. So the entrance dose is found by using equation 4.36. They said the MU delivered via the RPO field is 231, which is what we calculated up here. TAR at D max is 1.0, and using the equation 3.1, we do the inverse square factor. So the entrance dose of the RPO field is therefore this. If we look at the exit dose, we're using the factor here of 0.305 for this TAR. We're also saying that the inverse square factor is this, and therefore the exit dose turns out to be this. So the total dose at D max for the RPO field is 270 plus 64, and you end up with 334. For the LAO field, you go through many of the same calculations here as well. Adding them together, you come up with 507. So from this example, when the isocenter is offset away from the mid-depth, the weighting factor must be carefully selected in order to avoid very high doses in either Dmax region. In this example, equal weighting would further increase the dose of Dmax in the anterior oblique field and decrease the dose at Dmax of the posterior. Increasing the weighting factor on the posterior oblique would reduce the difference. So the general rule for selecting the weighting factor is to find the ratio of the TAR of the field and apply a similar ratio to the weighting factor. To achieve optimal dose uniformity between the two entrance points, the field with the highest TAR should be favored. Believe it or not, this gets more complex. So dose calculation for multiple beams with equal weighting. In a lot of cases nowadays, I'm not so sure that the isocenter is really used in order to be able to do this, but for the sake of this particular problem, we'll go ahead and use that. So in this example, a patient is treated via a 4-field technique using a 4 MV linear accelerator. The isocenter is at 80, and each field is 10 by 15. The prescribed dose is 200 centigrade at the 95% isodose line. The centigrade per MU is 1.025 for each field, and the dose is normalized to 100%. TAR for fields A and B is 0.793 for field C and D, it's 0.645. We're going to go through the calculations here for the MU. We'll find out here for A and B, it's at 65 MU per field. For C and D, it is 80 MU per field. This is a situation that we're talking about is much similar like what we saw in the previous, one of the previous figures. A and B is coming in this way, C and D is coming in this way. Isocenter is here. The 95% line is right there. And each field is going to be weighted 25%. If we want to make things more complex, we can do unequal weightings, where this is contributing a third, this is contributing 2/3. If we look to do this for fields A and B, what we're going to do is we're going to take our computation here per beam. So we take 1/3 as opposed to 2/3, since we're looking at just one beam at a time and they're split evenly. And we've got our prescription dose up here, and then we've got all of our other factors here. We come up with 86 MU per field. And for C and D, since they carry a 1/6 of the total weight each, this is what we are coming up with. Beam attenuators is calculated precisely as another techniques and is not included here. So what we're seeing here is that our MU equation is becoming much, much bigger here. And what we're going to see here at the end, and this is something that I will create a short video on shortly, is that the MU, or the number of monitor units, is going to be the prescribed dose multiplied by whatever the mode of measurement is here, TAR, TPR, TMR, times the isodose line that we're going to go with, times the calibration factor, times the reference dose rate, times the area factor, times the tray factor, and times the wedge factor. All of these things are going into computing the MUs. And that is something else that we need to remember as we go through. And then when we come into doing extended distance, on top of all of this stuff that we have to remember, we've also got the inverse square factor added into that as well. So these are the types of problems that I will be going over here so that we'll have an idea as to how to work these.